There are several features in Kotlin that are still considered to be experimental, but a lot of them are great to opt into even before they stabilize. So in this video, we're going to look at the 5 experimental features that I often opt into in my own projects to see if you might want to do the same. Kotlin has been known for its concise and expressive syntax, but still there have been a few cases that have always felt kind of unnecessarily verbose. So for example, when you're referring to an enum entry, especially inside a when expression, you just want to write it like this, but it doesn't resolve the name, and instead you've got to qualify it with the name of the enum class like this. And that makes for a lot of repetition throughout the when block, which is unnecessary when we know that the values here are only ever going to be entries of this enum class. Now, of course, you can import the entries like this, but you got to import each one that you're using, or you can just, I guess, use a wildcard import like that. So sure, that works, but even then you could still get conflicts. Like here, when these two enums both have an entry named standard, we end up getting the compiler error here. So we could use a named import, obviously, to work around this, but this is getting pretty messy pretty fast. And that's too bad because for us, it's very clear that in this code, the standard only ever refers to the breed, and in this code, standard only ever refers to the leash length. Well, thankfully, we can work around this with an experimental feature named context-sensitive resolution. And with this feature, you can see we no longer need to qualify each enum entry with the class name. And we also don't have to import any of them. This file has no imports at all. With this feature enabled, Kotlin knows that the values here must refer to this enum, and the values here must refer to this enum. Now, enums are my favorite use case for this feature, but there are others. This also works with other static references like these nested sealed types. So in this code, order, refund, and support are all nested within the request interface, and each one implements that interface. And without this feature enabled, we would have to qualify these right here, or we'd have to import them. But since I do have this feature enabled, Kotlin knows that these 3 are nested subtypes of the request interface. And there are some other cases as well, like companion object properties that have the same type as their container. So in this code, the anonymous user instance is a companion object member of this user class. So this properly is resolved without needing to be qualified. So again, context-sensitive resolution applies to a few different cases, but I suspect that enums are going to be the most common. To enable this feature, just add the context-sensitive resolution compiler option to your Gradle build file like I'm doing here. If you want to read more about this feature, I'll include a link to the keep document for it in the description of this video. All right, here's another experimental feature that cuts down on noise in our code. In a lot of languages, it's possible to write out a collection as a literal just using brackets and commas. So if you're calling a function that expects a collection, you could just call it like this. And this is JavaScript code, but it's the same idea in a lot of programming languages out there. But in Kotlin, we've had to call a factory function to create our collections. So things like list of, mutable list of, or set of. Well, in Kotlin 2.4, you can opt into the collection literals feature, and you can get a syntax that's very familiar to anyone coming from those other languages. We can just use brackets and commas like you can see I'm doing on these lines here. And the exact collection type that's constructed depends on the expected type. So even though each of these 3 new function calls is using a collection literal, each one is creating a different collection type depending on what was expected. So in other words, this one creates a regular list, this one creates a mutable list, and this one creates a set. And if there's no type specified at all, it just defaults to a regular old list. Now on the surface, this feature seems like it might just be saving a few keystrokes for a function call, but in some cases it can actually introduce some resilience. So for example, let's say that we update this function that expects a set so that it now expects a list like this. Well, our call sites that use a factory function will need to be updated. So you can see we broke the line right here, but the change is actually transparent to the call sites that used a collection literal like this one. Now, I'm not saying that this is a pervasive use case or that coding agents couldn't hammer out that change quickly, but still, it is an interesting characteristic of this feature. If you want to opt into this one, just add the compiler option like I'm doing right here. So context-sensitive resolution and collection literals are both designed to make your Kotlin code more concise. Next, let's take a look at a few experimental features that are focused more on ensuring that your code is correct. Destructuring has been one of my favorite features in Kotlin, but one of the disadvantages is that small changes can rewire your assignments in unexpected ways. So here I'm using destructuring to assign these data class properties to individual variables, but you might have noticed a bug. The minutes and year values were accidentally switched around, so this movie looks like it was made thousands of years ago and has a runtime of over 2,000 minutes. And the problem here isn't limited to writing the variables in the wrong order. So even if we fix this code like this, it's still susceptible to this problem if we were to insert a new property in the middle of this data class constructor. This would throw off the assignments at our destructuring sites. The cause of this problem is that destructuring so far has been based on position, but Kotlin 2.3.20 introduced name-based destructuring, and when this feature is enabled, our destructuring assignments are based on the name of the variables rather than on their positions. I went ahead and enabled the feature, and this time when we run it, the components are going to be assigned to the right variables, even when the variables are declared in a different order or when we insert a new property into the data class. And by the way, with this feature, your variables don't have to be named the same way as they are in the original components. You can use this syntax to give them a new name, and you can still be explicit about which component it's referring to. So when we run this, we'll see the values are still assigned to the right variables. And even with this feature enabled, you can still use the position-based destructuring when it makes sense. So for example, when you want to pull elements out of a list, well, the position-based destructuring could be exactly what you want. And in that case, you can just use this syntax with brackets instead of parentheses. To opt into this feature, just add the name-based destructuring argument. And for this one, you have to assign it one of 3 different modes. And here you can see I'm using the complete mode, but I've got a video that goes into a lot more detail about this feature, including all of the options. So I'll link to that in the description in case you want to dig deeper. All right, here's another experimental feature that's designed to help make sure your code is correct. Most of the time, when we ignore a value that's returned from a function, we're introducing some risk, and in the worst case, it could be an outright bug. So for example, in this code, I'm sorting a list of books, but when I print them out, you're going to see that they're actually not printed in the sorted order. They're printed in their original order. And the reason for this bug is that I'm using the sorted function, which returns a new list rather than sorting an existing list. So either we would need to make this a mutable list and call the sort function instead of the sorted function, or we could keep it as a regular list, but then we would need to assign this sorted result to a new variable. And unfortunately, there's nothing here telling us that this is going to be a problem at runtime. Well, to help with this, we can enable a feature called the Unused return value checker. And yeah, that's a big name, but the idea is simple. We get a compiler warning when we don't use a value that's returned by a function. So here I've enabled the feature, and you can see that this lights up with a warning. And that's not just here in the IDE, but it also shows up in the compiler output as well. So for example, your build servers would see this on their command lines. If you want to opt out of this warning at a particular call site, like in this code, it would be perfectly fine for us to ignore this warning. Well, in those cases, we can just assign it to an underscore like this. And if we're writing a function that has a result that we know can be safely ignored, we can just annotate it with @ignorable return value to suppress the warning at all the call sites, so we would no longer need to assign it to an underscore everywhere. So you can opt into this one with a compiler argument named return value checker, and just like with name-based destructuring, it has a few different ways that it can be configured. And in case you're interested to learn more about those options, I've got another video where I go into a lot more detail about it, and I'll link to that in the description below. All right, this last experimental feature is particularly helpful when you're writing concurrent code, especially in a multi-platform project. I'm talking about atomics. When you've got code that runs concurrently, it's entirely possible that you could end up with race conditions. The simplest example of this, of course, is just a counter where you simply add to it from a lot of different coroutines. And when you do that, you end up getting a number that's less than what it was that you expected. And there are lots of ways that you can safely manage race conditions in Kotlin code. And for simple values, atomics can be a great choice. Up until recently, you probably would have reached for atomics in the Java API, or maybe you would use the atomic foo library. But since Kotlin 2.1.20, you can use the standard library's common atomics. And to do this, just replace your mutable variable with an atomic type, like this, and add the import. And this one's a library feature rather than a compiler feature, so we just add the opt-in annotation like this. And you can see up here, there's an import for the +assign function, and that makes this operator right here work exactly like we would expect. So when we run this now, we're gonna see that we get the total that we expected. Now, typically when you're reading from the value of an atomic, you would use the load function like this, but its toString function returns the integer as a string anyway. So in this case, it's not really needed for the code right here. Now, as I mentioned, there are several ways to eliminate race conditions. I've got a video where I cover some other options as well, so I'll link to that video in the description below. So those are 5 experimental features that I think all Kotlin developers should consider opting into. If you've got experience with them, let me know what you think about them in the comments. And I'm sure that the Kotlin team would also love to get your feedback while these features are still experimental. As I've mentioned, I've also loaded up the description of this video with tons of links so that you can take a closer look at each of these features. But as always, actually playing with the code yourself is going to be the best way to explore. All right. Hey, thanks so much for watching this video. Remember to like the video, subscribe to the channel, and get enough exercise.